The purpose of this video is to help you speed up your differentiation for core 3. Now just say you were going to differentiate something like this. Y equals 2 sine of 3x. Now it's entirely possible for you to use the chain rule where dy by dx is equal to dy by du times du by dx. And I'm just going to do this using the chain rule so that you can see how it works. So first of all, you would make a substitution. So in the case of this, we would say let u equal 3x, and that would mean that y is equal to 2 sine u. Now, from that, we can get du by dx as 3, that's differentiating that, and dy by dx, pardon me, dy by du, very easy to lose track here, you've got to keep track, du would be equal to 2 cos u. And then we use a chain rule, so that would mean dy by dx is equal to dy by du, that's this one, 2 cos u, and we'd multiply that by du by dx, which is 3, so we would end up with 6 cos, and u, of course, is 3x. Now, that is absolutely fine, and you need to be able to do that, especially if you get yourself confused or in a bit of a pickle. But really, we want you to be able to do it a lot quicker than that. We want you to spot the general rule, and that's what I'm about to show you. So here are some general rules to start with. So you'll notice that I'm going to start with the log function. So if y is equal to the natural log of a function, f of x, so that could be something like 2x, or it might be something a bit more complicated, it might be something like x squared, then the differential of that function is equal to the derivative of this over the original function. There's the rule for the natural logs. Similarly, if we had y as e to a function of x, and in this case e could be something like 3x, or it might be something like x squared plus 1, then dy by dx is equal to the differential of that function times e to that function. And that's another general rule. And a similar thing is true for the sine and the cos functions. So if y is equal to sine of f of x, then dy by dx is equal to the differential of that times cos of f of x, and similarly for cos. Now, if you have to remember these rules, you are just making this life a lot more difficult, because, in fact, it's negative, isn't it, for cos, so it's negative sine. Really, these rules come out of your practice. And you've probably already noticed these sort of rules springing up when you've used the chain rule a lot. So we're now going to go and look at how you use these in practice, because it's pretty simple when you get the idea. And this will speed up your differentiation so that you won't get stuck in the middle of more tricky problems. It's a bit like learning your times tables, being able to do things quickly and fluently. Here we go. So we're going to work through these using these rules. So y equals 3 times ln of x, so dy by dx is equal to, now ln of x goes to 1 over x, and so it's going to be 3 times 1 over x, which is that. Next one, dy by dx. So we differentiate what's inside the function, which gets us 4, and then on the bottom we put the original function there, which of course gives us 1 over x. A slightly surprising result, you might think, but one that turns up a lot with log functions. Okay, here we go, dy by dx equals, I look inside the brackets and differentiate it, I get 2x, and then on the bottom I put x squared. And of course we can simplify that to 2 over x. dy by dx, I look inside the brackets and I differentiate it, so I get 2x, and on the bottom goes the thing in the brackets. And that can stay as it is. And if you were at any point worried about it, you'd use the chain rule, which of course you practiced. So, watch these, very, very similar. So, y is 3 times e to the x. So, dy by dx, so we keep the 3, and then we differentiate e to the x, and we get e to the x. It's a unique function. Next one, dy by dx. We look up here, we differentiate it, and we get 2, and then it stays as e to the 2x. You could look at this one as having looked up here, and it's the differential of x is of course 1, so it's 3 times 1, so it's the same rule. Third one down, dy by dx. We look at the function and we differentiate it, it's 2x, and then it's e to the x squared. Notice with e to the x, the same thing on the end every single time. And here, of course, the thing on the end of the every time is the 1 over x, or the 1 over what's in the brackets, because that's what the differential of ln is. It's 1 over whatever's inside. And the last one, dy by dx equals, and we differentiate it, what's inside the brackets, which gives us 2x, and then e to the x squared plus 1. And as I say, you can verify any of these with the chain rule, and you should be able to, because there will undoubtedly come the ones where you're not sure if this is right. Okay, similar thing for the sine function. So, dy by dx, we look in here, we differentiate it, and we get 3, and then sine goes to cos, so it's 3 cos 3x. Second one, dy by dx. Okay, we look inside it, and we've got x squared, so we differentiate that, and we get 2x, but this time we're going to multiply it by the 2, so it comes out as 4x, and then of course sine goes to cos, and it's x squared, dy by dx. Okay, we look inside, it's an x, we differentiate it and get 1, so we've got 1 times 4, and of course sine goes to cos, like so. Over here, we're going to do the same thing, so we go dy by dx. We look inside the cos function, differentiate it, and that gets us 4, and cos goes to minus sine, and it's 4x. dy by dx. Okay, it's cos, so it's going to go to negative. If you remember in advance, it means you leave room for your negative. Look inside the brackets and differentiate it. That goes to 3, but we multiply it by the 7, so it's 21 sine 3x plus 1. Next one here, dy by dx. Okay, we've got the 3 outside. The cos is going to give it to a minus sine. So we look inside the brackets and we differentiate. That gets us 4x times 3 is 12x. And then the cos goes to the minus sine, and it's 2x squared. My advice to you would be to do a pile of these, maybe even these ones, and check them with the product rule, the chain rule, just to make sure that you're doing them right. Okay, and the same thing applies here, really. So we've got here dy by dx equals, and we look inside the brackets and differentiate it, and that gets us 2x. We bring the power down, and then we've got the original brackets to 1 power less, which simplifies up to 14x, 2x plus 3 to the power of 6. and you can't multiply these things into the brackets because this is not a normal bracket. This is a to the power of 6. Just think of it. If you multiply that out, you'd have a power of 6, a power of, you have a massive long load of things. You can't just multiply the 14 in. Okay, this one here, we're going to write this in index form first. So it's 7x cubed minus 4x to the power of a half. Now it's in index form, we can differentiate it. dy by dx equals, okay, differentiate what's inside the brackets. That gets us 21x squared minus 4. Bring the half down. And then we have the brackets, 7x cubed minus 4x, and we subtract 1 off the power. Of course, that will tidy up. And then the last one. So this one here is already in index form, so we can go straight for differentiating it. dy by dx equals, and we differentiate what's inside the brackets, which is going to be 28x to the power of 3 minus 2x. We bring the power down, and then we write the brackets to 1 less. So 3 halves minus 1 is 1 half. And of course you can tidy that up. So, long and short of it is, you really want to be able to do simple differentiation like this without using the whole of the chain. Why? Well, because it's a lot faster and it means that you won't get confused in the middle of a bigger problem when you're trying to do this as part of something else. Hope it was helpful. Please give me any feedback. I appreciate it.